So in this section, we're looking at Hamilton paths and circuits. There's some information about William Rowan Hamilton in the book if you're interested in learning more about him. But essentially, this section really focuses on how Hamilton paths help us determine and solve transportation problems. And so here are two examples we might want to consider. In the first one, we have John is a traveling salesman for a pharmaceutical company. His territory includes 5 cities, and he needs to find the least expensive route to the cities and home. He wants to find the route with the minimal cost. So you can see that these routes are labeled with numbers. That number is implying the cost that it is to travel along that route for whatever reason. Perhaps that's the amount of gas you would use, perhaps it's gas plus toll roads, etc. Scenario 2, you have a mail truck must deliver packages to 5 different homes, A, B, C, D, and E. The trip must start and end at A. The graph below shows the distances in miles between locations. We want to minimize the total distance traveled. So in the first example, we want to minimize the cost. In the second example, we want to minimize the total distance, but we must also start and end at A. So we're looking at two different situations here, and here's what we want to consider. We're not even answering any questions about this yet, aside from the fact we want to consider these two scenarios and determine, does each scenario require that we examine paths or circuits where each vertex or each edge is traveled? So in both of these, we want to make sure that each vertex is traveled. The salesman must go to each of those cities and back to home. The mailman must deliver the packages to all of those houses. So therefore, each vertex must be traveled to, but you do not have to follow along every single edge. So then looking at part B, we're considering our answer to part A. We need to go to each vertex, but we don't have to travel each edge. But this is a very curious question. It says, for maximum efficiency, should you travel these once or more than once? And so you can think about it looking at the second example. We know we must start and end at A. We want to minimize the distance, and the numbers on each of those edges represents the distance. So if I start at A, the one I'm going to want to go to first, just based on this least number of distance between them, would be from A to C. And so that gives us 7 miles. And then from C, I'm going to want to go to D because that's 2 miles. Then from D, I'm going to want to go to B because my other option would be go to E, but that's 24. And to get to B, it's only 6. So I'm going to go to B, which gives me 6 more miles. And now here's where it gets tricky. I have to go to E. So from B, I need to go to E, which gives me 14. But your gut instinct might tell you once you get to E, you know you have to end at A. So most people might say, we'll go from E to A, but that's 29 miles. If I go from E back to B, that's 14. And then from B to A is 9, and I've gone back to my beginning. And 14 plus 9 is less than 29. So that would actually decrease the number of miles we need that we would have traveled by backtracking and going from B to E and then E back to B before going to A. So could I or should you travel these once or more than once? And it depends. Okay, it depends. You have to look at the situation. So thinking about that, we're going to go into what is a Hamilton path and circuit. So looking at the definition of a Hamilton path is a path that contains each vertex of a graph exactly once. A Hamilton circuit is a path that begins and ends at the same vertex and passes through all the other vertices of a graph exactly one time. So here's the problem with my example right here. I went through B twice. So that would not be That would have minimized the total distance, but that would not have been allowed for a Hamilton circuit because we're only allowed to go through each vertex exactly one time. Okay, except for the last one where we begin and end at it. So in this case, I would want to, once I get to where you said A to C, C to D, D to B, and then B to E, then we have to do E to A in order for it to be a Hamilton circuit. Okay, so true or false questions. A Hamilton path must pass through a vertex only once. That is true. I'm going to skip to C. It says a Hamilton path must pass through each vertex. That is true. D, a Hamilton path must pass through each edge. That is false. Okay. Unlike a Euler path, a Hamilton path, you do not have to pass through every edge. However, based on the nature of going to each vertex only once, a Hamilton path must pass through an edge only once. That must be true. So it doesn't have to go through every edge, but if it goes over an edge, it can only go over it once, because if it goes over it again, then it goes back to and repeats a vertex you've already gone through. So we're going to use the graph to answer the questions. We're going to say true or false. We're going to go through each one of these and determine, is it a Hamilton path or is it a Hamilton circuit? So for the first one, A, B, F, I, K, E, G, L, J, H, D, C is a Hamilton path. So remember, we start at the first vertex and then connect them. So A, B, F, I, K, E, G, L, J, H, D, C is a Hamilton path. It went through every single vertex exactly once. So yes, that is true. That was a Hamilton path. Let's do the same thing for B. We're checking to see if this sequence is a Hamilton circuit. So we're starting A, G, L, J, K, E, F, I, J. I can stop right there because look, I repeated a vertex, and based on the definition, it says a path that begins and ends at the same vertex and passes through all other vertices of a graph exactly one time. Well, it went through J twice, so that is not a Hamilton circuit. All right, so question 5, example 5, we're going to look at this graph and determine if there is a Hamilton path that begins at A and ends at B. So let's start. Let's do A to D, D to G, G to E, E to C, C to F, F to B. It went through each vertex once. That is a Hamilton path. Now, there could have been another one, okay? There could have been another one, but that is the one that I saw first. You could have gone A to F, F to C. Maybe not, because then you would have gotten caught up here. C to E, E to G, G to D. You couldn't get back to B. So never mind. Maybe that's is only one. Sometimes this is like a trial and error kind of situation. Okay, so number 6, we're looking for a Hamilton circuit that begins as A, B, and then we're going to continue it on. So if it's a Hamilton circuit, it needs to go through every vertex. It needs to start and end at the same vertex, which they told us will be A. And let's do it. So starting from A, we're going to go to B. From B, I'm going to go down to E. The reason why I don't go to D is because in order to, we would essentially be cutting off E and access to E without going through B or D again. So first we're going to do A, B, E, then go over to D. We're going to go down to F, up to C, and over to A. And that is a Hamilton circuit. All right, we're going to look at another definition. The next definition is what it's a complete graph. A complete graph is a graph that has exactly one edge between each pair of vertices. Are the graphs below complete? So That means so if I have A, B, C, and D, that there is exactly one edge between each pair. So A has to be connected to B, C, and D. B has to be connected to A, C, and D. D must be connected to B, A, and C must be connected to A, B, and D. And we have connections for all of those, so yes, that is complete. Now, this second graph on the right is not complete because if I look at point A, it's connected to B and D, but it isn't connected to C. And so therefore this is not complete. I had to sneeze, sorry guys. All right, we're going to look to see if we can find Hamilton circuits that go through vertex E only once in each graph. So let's see. Once I go here, if I start at A, I can go A to B, B to E, but here's the problem. If I go to then D and C, I can't get back up to A without going through E again, and that's not allowed. So no, we can't do that. Is this a complete graph? No, because there's not a connector between each pair of vertices. There's not an edge between each pair of vertices. And this had 5 vertices, A, B, C, D, E. Okay, now let's try again through here. Let's start at B. Let's do B, A, C, D, E, B. So yes, this does have a Hamilton circuit, but it is not a complete graph. There's not an edge between B and D. How many vertices are there? There are 5. Let's look at this last one. This last one doesn't have an E vertex, so it's just asking, can you find a Hamilton circuit for the graph? So can we start at one vertex and end up at the same one, going through each vertex exactly once? So I could do A to C to B to D to E. That would work. Or I could go A, C, D, B, A. That works. So yes, you can do that. Yes, this is complete because every vertex is connected to every other vertex with one edge, and there were only 4 vertices on this one. So then asking the question, did some or all of the complete graphs have Hamilton circuits through them? Well, there was only one example of a complete graph, and it did have a Hamilton circuit, but it did not have a vertex E. Okay. So now we're going to go through these. Can we find Hamilton circuits that go through, can we find a Hamilton circuit that goes through each vertex? Not E, just each vertex, only once in each graph. So let's look at this one. If I started at A, can I get back to A going through each other vertex? So I go to B and then I go to C. I cannot get back to A. So I cannot make a Hamilton circuit, not just through E, just at all. Is this a complete graph? No, A and C are not connected. The number of vertices was 3. This one here, I have A to B, B to C, C to A. Yes, I can make a Hamilton circuit. Is it a complete graph? All the vertices are connected to each other? Yes. And there were 3 vertices. A to B, can I get back to A? I cannot without going over that edge again. And so, no, I cannot make a Hamilton circuit. It is a complete graph. There are 2 vertices, but there's no Hamilton circuit. So then it asked, did some or all of the complete graphs have a Hamilton circuit? Yes, the second one did. Examine all the graphs 3 or more vertices. So that's even going back here. Were there any with Hamilton circuits? Yes, there were. Okay. Examine all of the 3 graphs with less than 3 vertices. That's only this one. Were there any Hamilton circuits through in that example? No. So looking at those previous examples, I hope you kind of noticed this yourself, but 2 characteristics that will guarantee a Hamilton circuit is if you have a complete graph that also has more than or equal to 3 vertices. Okay, so those 2 conditions will guarantee that you can find a Hamilton circuit. So let's look at these. First off, complete graphs always have a Hamilton circuit. We definitely saw an example that because if we only had two vertices, then you cannot get a Hamilton circuit because it would have to go over the same edge twice. So that's the only case where I have a complete graph that does not have a Hamilton circuit. If there's three or more vertices and it's complete, it would have a Hamilton circuit. Complete graphs never have a Hamilton circuit. That's false. We've seen examples that did have a Hamilton circuit. Incomplete graphs always have a Hamilton circuit. That's not true. That is false. We had an example right here. It was an incomplete graph, but it did not have a Hamilton circuit. Incomplete graphs never have a Hamilton circuit. Well, that's not true. We had an incomplete graph right here, but it did have a Hamilton circuit, so that was false. Incomplete graphs have a Hamilton circuit. There we go. A graph with three or more vertices will always have a Hamilton circuit. That is false. We saw the example that looked like this, A, B, C. That was I had three or more vertices because it had three and then did not have a Hamilton circuit. So all of those statements are false. Consider the graph and the circuits below. Are they Hamilton circuits? Are they distinct circuits? Okay, so the first one is C, A, B, D, C. That is a Hamilton circuit. Let's check the second one. I'll do the second one in yellow. A, B, D, C, A. That is also a Hamilton circuit. Goes through each vertex exactly once. Are they distinct circuits? Do they go through different edges? That we would answer by saying no, they went through the exact same edges. So it's not a distinct circuit. So there is actually a formula to determine the number of Hamilton circuits in a complete graph. If I have n vertices, the formula is n minus 1 factorial. So if you have 5 vertices, you would take 5 minus 1 factorial. So that'd be 4 factorial, so it'd be 4 times 3, which is 12, times 2, 24, times 1, 24. So we can actually answer what number of Hamilton circuits each complete graph has with the given number of vertices. So for 6, I would have 6 minus 1 factorial. That equals 120, because that'd be 5 factorial. For B, we would have 4, so 4 minus 1 is 3 factorial, which gives us 6. This one, we're determining if the graph is guaranteed to have Hamilton circuits. If so, determine the number of such circuits. So in this case, we have an incomplete graph. Not all of the vertices are connected. So it is not guaranteed. It is not complete. So we do not have to check that one. The second one is a complete graph. So what we do is we count the number of vertices, 1, 2, 3, 4, 5, 6, 7. So there's 7 vertices. So to figure out how many unique Hamiltonian circuits there are, we take 7 minus 1 factorial, which equals 720 Hamilton circuits. We're going to move on to take a look at weighted graphs. A weighted graph is a graph whose edges have numbers attached to them. These are like the examples that we saw with the traveling salesman and with the mail truck. And what we do is we can use the weighted graph to answer the questions that are asked about it. So we want to find the weight of the edge CE. So we would find from C to E, that weight was 21. Find the total weight of the Hamilton circuit. So AB is 6. BF is 18. F to G is 15. G to D is 18. D to E is 11. E to C is 21. And C to A is 21. And we just add those up, which gives us 110. So the answer for that, the total weight for that Hamilton circuit is 110. So this ties into the idea of traveling salesman problems. A traveling salesman problem does not necessarily have anything to do with salesmen or making sales. It's just a way to describe a type of problem that involves the same kind of process and thinking as a traveling salesman might consider. So what we want to do is we want to define the traveling salesman problem. That's the problem of finding a Hamilton circuit in a complete weighted graph for which the sum of the weights of the edges is a minimum. Such a Hamilton circuit is called the optimal Hamilton circuit or the optimal solution. And the optimal solution is the Hamilton circuit that gives you that minimum. Okay, so the diagram below shows the distances in miles between four cities, A, B, C, and D. A businessman must travel between all four cities, starting and ending at his home city, A. So we're starting from A. He wants to find the optimal tour. In this case, what is the cost variable, or the quantity we want to minimize? It tends to be the distance traveled that you want to minimize. Okay, typically you want to minimize distance, or you want to minimize cost, or you want to minimize time. But because these weights are shown in miles, you want to minimize that distance that's traveled. Just this brute force method before we actually attempt one of these. A brute force method for a traveling salesman problem is literally looking at all the possibilities and calculating the cost variable in each of the scenarios. So what you do is you model the problem with a complete weighted graph like the one up in this example. You make a list of all the possible Hamilton circuits. You determine the sums of the weights for the edges of each of those Hamilton circuits, and then the Hamilton circuit with the minimum sum of weights is the optimal solution. And it asks the question, does the brute force method guarantee the optimal solution? Yes, because you'll see all of the solutions possible. And so it will guarantee that you get the optimal solution. However, sometimes it takes quite a while. Now, in this example, this previous example, there were four vertices. So there's 4 minus 1 factorial, or we could say 3 factorial options for paths, which gives us only 6 paths. But imagine if you had 10 vertices. So you'd be dealing with 9 factorial, which is a rather large number, to list them all out and then calculate all of those possibilities. Let's take a look at an example. We have a delivery truck must deliver furniture to 4 locations, A, B, C, and D. The trip must start and end at A. The graph below shows the distances in miles between locations. We want to minimize the total distance traveled. Is the graph guaranteed a Hamilton circuit? Explain. Yes, there are 4 vertices and it's complete. So therefore, yes, it is guaranteed. It met the requirements to have a guaranteed Hamilton circuit. How many Hamilton circuits are there? Well, there's 4 minus 1 factorial, which equals 3 factorial, which equals 6 Hamilton circuits. When we list out all the possibilities, should I list the combinations or permutations of the last 3 vertices? We would end up wanting the permutations of the last 3 vertices. We want to make sure that each one gets included. So if we're starting and ending at A, you want to make sure that you permute the remaining vertices. So we're going to use the brute force method to find the optimal solution. So here's what we know. We must start with A each time. Okay, and so when you think about this, we're going to start from A. And so one first thing that we could do is we could go to B. But from B, we have two options of where we could go to. So I need to have two possible circuits that start with AB. I could also start with A going to C. But when I go to C, I would have two options for which way I go. So I need two that start with AC. And then same thing, I could go from A to D, but from D I have two options of where I go to, so my second value would be to D. I need two options that start with AD. Then from there, we're going to go to the remaining option choices. So if I use AB, then I could go to C next or I could go to D next. But if I go to C next, then I also need to go to D and then back to A. If I go to D third, then I need to go back to C and then end at A. So you see how we get those different. I continue on, and I'm again from AC, I could go to B next or I could go to D next. If I go to B next, then I still have to go to D and then back to A. If I go to D next, then I would have to then go to B and then to A. If I started going from A to D, then I have two options following D. I could either go to B or I could go to C. If I go to B first, then I still have to go to C and then go to A. If I go to C first, I would still have to go to B and then go to A. So we end up getting those 6 possible Hamilton circuits. Then we add up the cost for each of those circuits. So A to B is 10 from the graph, B to C is 6, C to D is 2, and D to A is 4. So I would add that up. That gives me 22. 10 plus 6 plus 2 plus 4. All right, for the next one, we have A to B is 10, B to D is 3, D to C is 2, and C to A is 5. So 10 plus 5 plus 5, we add those all up and we get that that's equal to 20. Doing the next one, A to C is 5, C to B is 6, B to D is 3, and D to A is 4. So that gives us 10 plus 8 is 18. Let me go A to C, which is 5. Let me use a different color. A to C, which is 5, C to D, which is 2, D to B, which is 3, and B to A, which is 10. That gives us 20. Then we have A to D, which is 4, D to B, which is 3, B to C, which is 6, and C to A, which is 5. So that gives us 10, 18. Perfect. And then lastly, we have A to D, which is 4, D to C, which is 2, C to B, which is 6, and B to A, which is 10. And that gives us 22. So we have two Hamilton circuits that give us 18, which is our minimum distance. It could be ACBDA or ADBCA. I'm running out of time on this one, so I'm going to kind of give you a little hint for this. Um, when you have a lot of vertices, you get a lot of possible routes. And so therefore, it's unreasonable to try and attempt to do those with the brute force method. And so that's what this question is getting at. If you want to do the math to check it, please do so. But I wanted to look at the nearest neighbor method. This gives you approximate solutions as opposed to an exact solution. So the nearest neighbor method does not guarantee an optimal solution. However, you can model the problem with a complete weighted graph and identify the vertex that starts as the starting point. From that starting point, choose the edge with the smallest weight and then move along this edge to the second vertex. If there's more than one edge with the smallest weight, choose either one. From the second vertex, choose the edge with the smallest weight that does not lead to a vertex already visited, and then continue this on.